Now, to actually lay out our PCB, and in my opinion, this is the fun part, we can get to that menu in a couple of different ways. We can go back to our KiCad main menu right here and click on the PCB editor. We can double click on the .kicad underscore PCB file right here, or directly from our schematic right here, we can click on this little button up in the top right that says switch to PCB editor. I'm going to click on that, and if you give it a second, you'll see that our layout file opens. This will look very similar to your schematic at first, or your schematic editor at first, but that's about to change very fast. Let's talk about all of the different fields on our PCB layout editor. So, of course, in the center, we have our actual PCB layout document. This starts out completely empty except for the blank table of just metadata information about your design in the bottom right. Then we have a properties menu that is currently empty over on the left. We have a whole bunch of buttons in our toolbars on our left and right side. And then we have a layers menu on the right hand side. Now, what are layers on a PCB? Well, a board like this one has copper not only on the surface, but also on the back. It can even have internal layers where you can have more copper traces routed on the inside. This is equivalent to, on our breadboard, having wires running inside of the breadboard itself. Because of that ability, we can have a whole bunch of really complex circuitry built onto a single, very small board with potentially thousands of wires in a couple of square inches. So with more complex boards, we can add more layers as we need. Now, what are these other layers that we're seeing? Well, adhesive, paste, and mask are all used for telling the PCB manufacturer which parts of the copper need to be exposed to solder components to. The adhesive and paste are, solder paste, which is where basically a tacky glue-like substance is laid onto the board before a component is stuck down in it. It's then thrown into an oven where that glue melts and turns into actual metal, and it hardens to keep those components in place and form a solid electrical connection. The mask element is this green coating on the surface of the board that protects all of the internal copper from accidentally shorting out against other things or potentially being scratched off or damaged. We also have a bunch of other layers on here that are used for various purposes. Courtyards, for instance, are used to indicate where the edge of a component is to make sure that things don't overlap. Margins do roughly the same thing. The fab layers for fabrication, the user layers, the eco layers, and the drawings and comments layers, all of those are used purely for reference. They are not actually printed onto the board anywhere. They're not used for drawing or cutting anything on the board. They're not used for electrical connections of any kind. The other one that is actually really important for the actual layout of the board is the edge cuts layer. This one defines the outline of the board. It is the shape of the board that will be cut out of a much larger wafer, and it also indicate where holes are that need to be drilled in the board. So if we wanted to cut, say, these notches that I have on the edge of mine here, I would have to draw on the edge cuts layer those little notches so that the manufacturer knows to cut the notches out. We'll get into all of those a little bit more in a moment here. We can look at some of the other menus that are available to us, like the selection filter down here. We'll see that by default, almost all of these boxes are checked. We have all items, footprints, tracks, pads, zones, dimensions, text, vias, graphics, rule areas, and other items. Those are all of the different things that we can put on our board and move around and actually place in different areas. We don't always want to be able to move them at the same time. You'll again see how useful this is in a moment whenever we get to laying out our board. Just to finish introducing some of our menus here, we have objects, where if we want to make some things more visible and others less visible, we can adjust these sliders here. And we have nets, which are the various electrical connections that are made between different components on our board. Again, we'll come back to it in a second. Before we actually start putting our components on this board and drawing the connections between them, we need to set up the project, which is the actual physical layout of the project. This part does not really include the schematic that we worked on earlier. For this, we'll go over to File, and we'll go to Board Setup. And again, this has a whole bunch of menus nested inside of menus. For the most part, we can leave the board editor layers menu alone. The default values are usually perfectly fine. You'll see that the only two that we can actually edit here, aside from the user layers, are the f.cu and b.cu. These translate to front copper and back copper. By default, we only have two copper layers where we can actually route electrical connections. We'll leave those set to signal right now, though you can indicate if you want to use them for power or for both or so on and so forth. But more often than not, you can just leave it on signal. This doesn't actually change anything about the board that's being manufactured. It just is basically used for a bunch of diagnostics and tests that you can run to make sure that you're not accidentally connecting a power connection to a signal trace or so on and so forth. We'll talk about those in a moment. The super critical part that we basically always want to cover first is the copper layers drop down inside of the physical stack up menu. This is again indicating to KiCad how many layers of copper do we want inside of this narrow board. It's possible to include up to 64 sometimes, or some things go even higher. KiCad maxes out at 32. Now, I can tell you I've been working with these printed circuit boards for some time now, and I've never had to use more than a 32 layer board. And even that I probably could have gotten away with a 24 or 16. If you get to that point, then you are well beyond needing the information in this tutorial, because that will be a fairly advanced board. Now, I'm going to leave this on the default 2 copper layers, because for such a simple circuit, we could actually just get away with 1. But every printed circuit board by default is usually made with 2 layers, so we will just leave that there for now, and also so that I can show you what the advantages are of having multiple layers on your board. If you are getting some kind of specialty board manufactured, you can specify the exact thicknesses of each layer in millimeters here. You can also specify the different materials that they might be made out of, but for our purposes, we can leave these at the defaults. FR4 is the resin substrate that just about all PCBs are made out of, some variation of that material. It's a very electrically resistant material that allows you to have components on one side that are not at all shorted to the components on the other side. So once we've reviewed that and made sure that we're set to 2 copper layers, we can go on to some of the other things that we might need to change in here. Board finish, we can leave those as defaults. Solder, mask, and paste, leave them as defaults. We don't need to modify anything in the text and graphics menu. The design rules are super, super important. Let's go down to constraints under that design rules section. You'll see a bunch of fields that were given here. Minimum clearance, for instance, is what is the closest distance between 2 different sections of copper that we can have on this board. The reason this is important is because, say we have the positive and the negative connections to our LED on 2 separate copper tracks, 2 different traces, and they're right next to each other. If the minimum distance is set to maybe 0.001 millimeters, and they're very, very, very close to each other but not quite touching, then in theory, those traces will not be connected to each other. They'll be completely isolated from each other. But in reality, manufacturers of printed circuit boards can only print those boards with copper so far apart. So we need to figure out what manufacturer we're going to use and what their minimum clearance values are. So for this, you'll need to identify a manufacturer that you want to use first. If we're having boards manufactured by, let's say, one that I like to use is Aisler over in Germany, I'm going to look up Aisler manufacturing capabilities. And then one of the first results you get, or it's usually up near the top, let's see, technical capabilities. So they will typically tell you some of the specifications for your boards, like how far apart your copper has to be, but the very minimum. The Aisler tends to group these under the design rules section, so I'm going to go there. Here we go. So let's see if we can find the minimum clearance value. Minimum spacing of copper is what they call it, and it is 150 micrometers, which for us is 0.15 millimeters. 0.15, so we can fill that in. The next item is minimum track width. Again, certain manufacturers can only produce copper traces of a certain width or of a minimum width. So we need to make sure that our manufacturer is capable of producing whatever board we design. So they tell that to us, Aisler tells that to us right up at the top of this page. It's 0.2 millimeters. Minimum connection width. These ones I don't often have to modify quite as much. But let's see if they tell us. Minimum copper width, or minimum connection width. Most often this is the same as the minimum track width, so I'm just going to assume that that is the case and enter 0.2. Annular width and via diameters. To understand what these do, we have to understand what vias are. Suppose you have a copper layer on one side of your board and you have a copper layer on the other side. Say you have a wire that you want to run across the surface of the board and then punch through and come out on the back and then connect to a component on the back side here. For that, you need a tunnel that goes through the board connecting those two layers together. That tunnel is called a via. The via is structured like this little circle that they show here. Let me see if I can find a bigger image right here. It's structured as this circle, which is just a hole drilled straight through the board with a copper ring or a metal ring that lines the inside of that tunnel, basically forming a complete path for electricity to flow through the hole in the board. Now, different manufacturers can only produce different vias of different sizes based on how big their drill is, for instance, or what the how accurate the machine is that etches the copper on the board, that kind of thing. So we very much don't want to use, say, a 0.2 millimeter via if our manufacturer can only produce a minimum 0.3 millimeter. Otherwise, they might try to drill that hole and completely ruin something on our board design. So this is why we're specifying all of these values in the board setup before we even draw the actual board, because we need to make sure that KiCad is only creating connections that the manufacturer can actually produce on the board. So let's find first the minimum via diameter, which again on Aisler is through hole vias. Here we go. The minimum via drill hole is 0.3 millimeters for the drill. The minimum annular ring is 200 micrometers or 0.2 millimeters. So the annular ring is the copper ring that is around that hole of the via, and how thick it is on each side of the circle. You can kind of see that in this diagram that they give us on Aisler. So we know that the annular width here is 0.2 millimeters, which is actually kind of large. A lot of other manufacturers go down to 0.1. The minimum via diameter then, since we know that the drill size is 0.3, and then each side of the annular ring needs to be 0.2, then the total diameter is 0.3 plus 0.2 plus 0.2. So that's 0.7 millimeters in total. 0.7, and that should be good. The copper to hole clearance also is usually on here somewhere. Spacing NPTH is non-plated through hole. So a hole to copper is 0.25 millimeters, which should be good for here, which is the default in KiCad as well. Copper to edge clearance, 0.3 millimeters. All right, now the hole size. Again, this is the incredibly tedious part of setting up our board parameters beforehand. But if we do this once, then we can just copy and paste these values into any future PCB designs, or even set up a template inside of KiCad that makes it so that we don't have to fill these values out manually every single time. And that's really useful to us, especially if we tend to order from one manufacturer all of the time, which I do. And Aisler is one of those that I use very frequently because they are relatively affordable as well, and their boards are very high quality. So the minimum through hole is usually the same as the minimum via hole size, which was down here. Minimum via drill, which is 0.3. Hole to hole clearance, do they give us that? If not, I'm going to assume that it's the same as the non-plated through hole, so 0.25. And then U vias, this is a micro via. That is a whole other ball game that we're not even going to cover so much in this class, just because that is a type of via that's used on much more advanced printed circuit boards that you're probably not going to get to for some time. Basically, it's just micro vias are just extremely, extremely tiny vias that only punch part way through the board rather than all the way through. So if you have 16 different layers, you can have vias that only connect the top 4 or something like that, rather than connecting all 16 together. As for the other values on these boards, you can usually leave them at a default. The silkscreen values, arcs and circle segments, we're not even going to be using circles, so that's completely fine. Now, the next thing that we're going to want to change here is the predefined sizes menu. We already determined what the smallest via sizes we can use are, which are a diameter of 0.7 millimeters overall and a hole size of 0.3. So we can use that for basically all of our vias. We don't have any reason to use some bigger ones than that, so I'll leave that as the only one. But the values that we're going to have to add here quite a bit are the track widths. Now, tracks are the actual wires on the board, right? They're the physical copper connections between one pin and another pin. And you may be wondering, why would we have to use different widths for those copper traces? Well, say we have our LED that is connected to this USB port. We've already determined that at most that LED can handle 20 milliamps. If we try to use a track or a trace, the vocabulary is interchangeable here. If we tried to use a track that was 0.001 millimeters, it would be extremely narrow to be able to carry 20 milliamps. Even though that's a small current, 0.001 millimeter tracks are very, very tiny. If you push a high current through a small track, you wind up burning it out, or it winds up getting very hot and damaging other things around it. So basically, what we're doing here is we're including a bunch of presets for different track sizes, so that if we need bigger tracks to carry larger amounts of current somewhere else on the board, we can easily switch between them. So what I like to do, since we already know that the minimum value that Aisler allows is 0.2 millimeters, I'm going to enter that, 0.2, and then I'm also going to enter a 0.5 for a higher current track. Now, if you want to know how much current each one of those track widths can carry, there are tons of tools that can help you with this. KiCad has some calculator tools built into it that we can find on its main menu, but there is one that I like to use more frequently, which is from Advanced PCB, which is a manufacturing company, called the Trace Width Calculator. It's the first link that shows up. So what we have to do here is we specify first how much current do we want our trace to carry. In this case, it's 0.02 amps, right? That's for 20 milliamps, 0.02 amps. And then what is the copper thickness? Now, copper thickness on a board is how thick is that physical layer of copper off of the board. This is measured in a variety of different units. The most common one is ounces per square feet, so it's more a copper weight than a copper thickness, but 1 is the most common, or say we want to cater for the worst case, 0.5. 0.5 is also used in some places. If you want to know for certain, you can go back to your manufacturer again, and they will tell you 35 micrometers. I'm not sure. I think, oh yeah, that does translate to 0.5 ounces per square feet of copper as well. So we were right in entering 0.5 for this value right here. Now, there are optional inputs like what is the maximum acceptable temperature rise? Like if I want to push 20 milliamps through this trace, how high can the temperature get? What would a reasonable temperature be? Well, I'll say the ambient temperature, the starting point, is 25 Celsius. You can also change this to Fahrenheit if you wanted. And I don't want it rising more than 10 degrees from that. And then how long is the track? Roughly. You can average here. I'm going to say that our trace or track will be at most 10 centimeters or 100 millimeters here. And immediately this website will tell you what the minimum trace width is. You'll see here the required minimum value is 0.007 millimeters. That's extremely tiny because our current is extremely tiny here. But say we were building a phone charger that's carrying up to 3 amps, right? We'd enter that new current value up here, and it would recalculate and tell us that we need a 7 millimeter wide trace to carry 3 amps of current while only increasing the temperature of the board by 10 degrees. That is a huge trace. That is very difficult to work with. So typically we will end up having to use a thicker copper or something like that. But that is why it's really important to calculate your trace widths ahead of time and specify them all in this board setup page in KiCad, because if you wound up entering only 0.2 here instead of giving yourself a wider trace width to use later on, then you wouldn't be able to account for that 3 amps, say, if you wanted to design a phone charger. So in this case, we've just found out that if we're only pushing 20 milliamps here, our 0.2 millimeter trace is going to be plenty. We don't need to use our bigger 0.5. So I'm just going to delete that one. We won't need that at all. So this is all that we'll need in this menu. The only other thing we might want to change is our net classes. This is what the default values are going to be for things like our clearances between holes, between traces, what the widths of our tracks are, how big our vias are going to be, so on and so forth. Typically, for your default, I would advise that you use the same values that you specified in your constraints section right here. So our minimum clearance was 0.15. Our track width was 0.2, via size was 0.7, via hole 0.3, and then we can ignore the micro via sizes, holes, and the DP width and gap. Those are for differential pairs. That is well outside the scope of this project and this class, but you will likely learn about it later if you're learning about routing high-speed signals like USB 3 or Ethernet or so on and so forth. But for now, let's finally move on from this and get to actually designing our board.